Welcome to the first semester of Organic Chemistry. My name is Dr. Pike, and I will be your host for this semester. We start off the course with Chapter 1 in Organic Chemistry by Maitland Jones. And Chapter 1 is really a review of some of the basic principles of general chemistry that you're going to need to know in order to understand the structure and reactivity of organic molecules. Now, we're going to actually start off talking about covalent bonds and Lewis structures. So if you're following along in the textbook, you'll notice that it's about partway through the chapter 1 that we begin. Now, that doesn't mean that you don't need to know the previous material. You certainly do. I simply think that it's something that you can refresh your memory on outside of the normal class time and or lecture series. So let's get into talking about covalent bonds and Lewis structures because this is a very important concept for you to understand as we go on through the semester. We demonstrate bonding between typically nonmetals using Lewis structures, right? So we learned about this in general chemistry really toward the end of the first semester of general chemistry, if you recall. Typically we are introduced to Lewis structures. And so I'm going to simply review some of these concepts and remember in a generic sense, if I have an atom A and it has an electron and it reacts with another atom B that also has an electron, then a covalent bond occurs in which atom A and atom B approach one another. And eventually they get within a distance that is stable. And we're going to talk about what happens in that process in just a little bit, thinking about hydrogen. But we know that they come in close proximity together and they share the two electrons. And so we say that is a covalent bond. And we simply draw that bond as a line between the two atoms. And so that represents a covalent bond. So this is very important to understand and distinguish between an ionic bond, right? Remember in an ionic bond, let's say B would give up its electron to A or vice versa, and then whichever gave up its electron would have a positive charge and the electron acceptor would have a negative charge. And so we are not discussing ionic bonding. Remember, we are discussing covalent bonding. So as an example of this, the simplest example obviously is hydrogen. How do we make hydrogen? Well, two hydrogen atoms come together. Each one has an electron. And of course, when they approach one another, they start to form a covalent bond between the two of them, sharing the two electrons. And we can demonstrate this as a Lewis structure with two electrons. Again, we typically don't draw the two electron dots between the two atoms. We simply draw a line between the two atoms. And so this would be the Lewis structure of hydrogen. And understand that when we're talking about hydrogen, we typically simply draw H2. And so these are two different types of representations of hydrogen. We have H2. We also have a Lewis structure, H with a bond, a line between the two hydrogens, right? Another example of this would be when two fluorine atoms come together. So fluorine has 7 valence electrons in its outer shell. And so drawing the Lewis dot symbols of fluorine, remember we draw 2 electrons on each side of an atom if we envision a box around that atom. So fluorine, having 7 electrons around it, has 1 unpaired electron. When 2 fluorine atoms come together, the 2 unpaired electrons are shared between the 2 fluorines, and then of course each fluorine has what we call 3 pairs of non-bonding electrons around it. And in general, the formula we simply write as F2. Now, we can also draw covalent bonds between atoms that are obviously not the same. So if I take hydrogen and fluorine and think about their Lewis dot symbols. H has 1 electron in its valence shell. Fluorine has, again, 7 electrons in its valence shell with that 1 non-bonding electron. And when they come together, the 2 non-paired electrons will come together to form a covalent bond. And we represent it like this. So this is the Lewis structure of hydrogen fluoride. Now, let's think about polarity. Hydrogen and fluorine are bonds that are nonpolar covalent. So they're covalent bonds. They share the electrons together. And they share them in a way in which the electrons are distributed completely equal between the two atoms, right? If we think about hydrogen fluoride, it is a polar covalent bond. And the reason for this is because, as we learned in general chemistry, fluorine has a higher electronegativity than hydrogen, and it attracts the electrons better than hydrogen can. So we say that more electron density resides on the fluorine than does on the hydrogen. Now we measure this using a dipole moment. So a dipole moment measures the polarity of a bond, and it depends on the electronegativity difference between the two atoms, again, as we learned in general chemistry. Another very important note is to understand that just because a molecule has polar bonds does not necessarily make it a polar molecule. A classic example of this is carbon dioxide. So if we look at the Lewis structure of carbon dioxide, I'm going to draw this out here. Oxygen is double bonded to carbon, which is double bonded to the other oxygen. There are 2 pairs of electrons around each oxygen. And so if I look at the polarity of the bonds, we know that oxygen is more electronegative than carbon. So we draw what's called a dipole moment in the direction of the oxygen. And that's denoted by an arrow that's pointing towards the oxygen. And then we have on the end of that arrow a plus sign, which denotes that carbon is actually a little bit electron deficient, right? So that oxygen-carbon bond is a polar bond. Now, there's also another polar bond, though, in the molecule. And it happens to be another carbon-oxygen bond. And it also happens that dipole moment is in the exact opposite direction as the dipole moment of my first bond. And because of this, even though the carbon-oxygen bond is polar, each dipole cancels one another out, and therefore the entire molecule itself, we say, is nonpolar. Right? So a very important concept to understand, especially when we're thinking about how molecules interact with one another. And we're going to see, typically you have maybe an area that's electron rich is going to interact with an area that is electron deficient. So one molecule may have an electron rich component, another molecule has an electron deficient component, and they're going to interact with one another. And we're going to explore that later on and throughout the semester. Okay, so one of the things that we really need to be able to do well is drawing Lewis structures. And drawing Lewis structures requires us to use valence electrons. And so you have to understand how to calculate valence electrons, and that's fairly easy. Again, a reminder that they are simply the electrons in the outermost shell, right? So let's take a look at a few examples. My first example is ammonia. ammonia, when we think about valence electrons, we have to think about the valence electrons of all of the atoms in the particular structure. So nitrogen has 5 valence electrons. Make sure you understand where I'm getting that number 5, right? It's in the second row. It has 2 2s electrons and it has 3 2p electrons. So that gives a total of 5 valence electrons. And of course, hydrogen only has 1 valence electron, but there are 3 of them, and so we have a total of 3 valence electrons from the hydrogens. If we add up the 3 and the 5, we get 8 total valence electrons. So how do we place those electrons around a particular structure? Well, one of the things we have to know is the connectivity, and so this comes certainly with practice. Understand that hydrogen can only ever be bonded to one thing, and so the nitrogen has to be bonded to each hydrogen, right, because the hydrogen's giving 1 electron, and so we say that, so we can draw a Lewis structure that looks like this, right, where the nitrogen is sharing a pair of electrons with each hydrogen, and that gives a total of 6 valence electrons, and then the 2 remaining valence electrons are on nitrogen itself, and we call these a non-bonding pair of electrons. And of course, we typically will draw it like this, showing the bond between the atoms of nitrogen and hydrogen instead of the dots, right? So I want you to draw this type of structure, not the structure on the left, when thinking about Lewis structures. So nitrogen has a lone pair of electrons. Always draw the lone pair of electrons, especially when we're starting out. This is going to be very important in understanding the flow of electrons, and you're going to see how this plays out later on in terms of drawing resonance structures, right? And so typically, when we're thinking about a Lewis structure, most of the time it's simply easier to draw the bonds between the atoms and then think about the remaining electrons. As an example of how we do this, let's take a look at phosphorus trichloride. So phosphorus is right underneath nitrogen. It also has 5 valence electrons. We have 3 chlorines, and so each chlorine has 7 valence electrons, and that means we have a total of 21 valence electrons from chlorine. So 21 plus 5 is 26 valence electrons. All right, so how do we place these electrons in the structure of PCl3? Well, phosphorus is the central atom, and so it has 3 chlorines bound to it, and so we're simply going to start off drawing the bonds between the phosphorus and the 3 chlorines. And we have to understand that each bond constitutes 2 electrons. So we have 3 bonds times 2, that's 6 bonding electrons. If I subtract those 6 from the 26, I get 20 non-bonding electrons that are left remaining. And generally speaking, you're going to start off placing the electrons around the most electronegative elements. So chlorine is more electronegative than phosphorus. And we're going to give each atom an octet of electrons. So we start off with having 3 pairs of electrons around chlorine. That's 6 electrons. And another 6 electrons is 12. And then another 6 electrons around the third chlorine is 18. And so we have 2 electrons left. We're going to place those 2 electrons on the phosphorus. And again, notice that now phosphorus also has an octet of electrons. It has 2 from the non-bonding pair of electrons, and it has 2 each from each bond, which is the 6. So 6 plus 2 is 8 electrons around it. And so it satisfies that nice octet rule. All right, so let's look at something a little bit more organic, and we'll take a look at methanol. Now methanol, you'll see, can be written CH₃OH. Sometimes it's written HOCH3. Now both of these tell you a little bit about the connectivity of methanol. And so one of the things that you're going to have to get used to is recognizing that oftentimes the formula can help you with connectivity. And I've discovered throughout the years that sometimes students have a difficult time thinking about how things are connected, and so sometimes these little tips are very important in the little things, right? So what do we have? We have carbon that's connected to 3 hydrogens. So that's what that means. The, CH3, there are 3 hydrogens connected to carbon. The oxygen is also connected to carbon, and then the hydrogen that's on the oxygen is connected to the oxygen. So we can draw a Lewis structure showing all the bonds, and this is what the Lewis structure looks like. Now, we have to make sure that we have all of our electrons. So again, we count our valence electrons. Carbon has 4 valence electrons. We have 4 total hydrogens, and so that's 4 valence electrons from that. And then oxygen has 6 valence electrons. We add these up and we get 14 valence electrons. Now, again, we count our bonds. If you count the bonds, 1, 2, 3, 4, 5, you have 5 bonds. Each has 2 electrons, and so that gives us 10 bonding electrons, which means there are 4 non-bonding electrons. And if we inspect the structure, hydrogen has 2 electrons around it. That's as many as it can have. Carbon has 8 electrons around it. That's as many as it has. Oxygen, on the other hand, has only 4 electrons around it. So we can place the remaining 4 electrons around the oxygen, giving it 2 pair of electrons. And now we've drawn the Lewis structure of methanol, right? Another simple organic structure, which we'll get into in Chapter 2, is called ethane, C₂H6. And again, for organic compounds, typically speaking, when you have multiple carbons, you know that you're going to connect those carbons together. And so the 2 carbons are connected, and then we place the remaining 6 hydrogens around them. Typically, you distribute the hydrogens evenly if you're not quite sure how things go, right? So each carbon gets 3 hydrogens, and you notice that right away, both carbons have 8 electrons around them, and all of the hydrogens have 2 electrons around them. So we shouldn't have to do anything else to this particular structure, but simply to verify, we can say that we have 2 carbons, which is each carbon has 4 valence electrons, so that's 8 valence electrons. We have 6 hydrogens, and so that's 6 valence electrons, and so we have a total of 14 valence electrons. If we add up all the bonds, how many bonds do we have? 1, 2, 3, 4, 5, 6, 7. 7 bonds times 2, all of the electrons are bonding. And therefore, we don't have to do anything else to this structure. That is the Lewis structure of ethane. Now, as a little twist, we can look at C₂H4. So this is called ethene or ethylene. Ethene is a formal name. Ethylene is a common name. We'll get into naming again in Chapter 2. And we're going to do the same thing here. We know we have an organic compound. We have 2 carbons. Those carbons are attached to one another. We're going to distribute the hydrogens so that 2 hydrogens are on one carbon and 2 hydrogens are on the other carbon. Now, when we look at the number of valence electrons, we see that the 2 carbons still have 8 valence electrons. Now we only have 4 hydrogens, and so that only gives us 4 valence electrons from the hydrogens. So we have 12 total valence electrons. Counting the number of bonds, we have 1, 2, 3, 4, 5 bonds. And so that's 10 bonding electrons, which means that there's a remaining 2 non-bonding electrons. And I'll say that in quotes because the question is, how do we place the 2 non-bonding electrons? If you notice, each carbon only has 6 electrons around it, right? So each carbon, as it stands, is deficient in electrons. It doesn't satisfy the octet. Now, we could put both electrons on one carbon, and that would give it 8 electrons, but the other carbon would have only 6. It would also give a formal charge for both of them, which we'll talk about later on. And so the easiest way to do it is to simply give 1 electron to each carbon. Again, though, each carbon isn't satisfied by the octet rule. So what do? Well, you create a double bond. So each carbon is going to share the 2 electrons together. And so we get a structure that looks like this, right? So now we have what's called a double bond. And we'll talk about the different types of bonds, but the 2 types of bonds between the 2 carbons, we have a sigma bond and a pi bond. And again, we'll get into that later on. And generally speaking, we draw ethylene like this. And the reason for that is because the carbons, each carbon is what's called sp2 hybridized. Again, we'll discuss that later on. And so the bond angle is 120 degrees. And that gives a better representation of that structure. So this is a little introduction to drawing Lewis structures, and of course we need to practice more and more to get better and better.